All right, folks, welcome back to our conversation of thermodynamics. Thus far, we've been trying to answer the question of why some chemical processes just happen or are spontaneous, whereas others aren't. And in our last discussions, we talked about enthalpy or the heat of reaction, and then introduced the idea of entropy, the amount of disorder or the amount of related to the amount of microstates that a system could possibly arrange itself in. And what we're going to do next is we're going to take those ideas of energy, being entropy and enthalpy, and put them together to answer that question of why something is spontaneous or not by using what's called Gibbs free energy, otherwise referred to as the chemical potential of a reaction. So let's get started. So, kind of as a refresher, right? Again, we're trying to answer this question about what determines spontaneity. So we have this question here, what determines spontaneity, entropy, or enthalpy? So let's remind ourselves of what the second law of thermodynamics says. In layman's terms, or kind of common language, the second law of thermodynamics states that energy will always flow from a more concentrated area or form to a less concentrated area or form. So we can think like thermal energy dissipating. We can think about particles in the universe scattering post the Big Bang. The way that we've mathematically represented this is that delta S of the universe must always be increasing. But in general, I like this idea of thinking about the second law of thermodynamics as energy will always disperse, because I think this allows us to answer this question in a very tidy way. So, what determines spontaneity? What determines if something will like result in energy net dispersing in the universe? So, the question was entropy or enthalpy. So, we know that if entropy increases, so if delta S of a reaction, not the reaction, delta S of the surroundings, and thus net delta S in the universe is increasing, then we are dispersing energy. And we would call this something that is spontaneous. However, we also have a way of dispersing energy, like we talked about thermal energy, right? So if the heat of reaction is exothermic, then we are dispersing thermal energy out into the universe, or at least out into our products, the surroundings. And this would imply that we are spontaneous. So then the question is, which is it, entropy or enthalpy? Because both can show a dispersal of energy. So the answer is it has to be both. So both the enthalpy of the system and the entropy of the system, which we express as the entropy of the surroundings, because it allows us to make this connection to the universe a little bit easier so we can follow that second law of thermodynamics. These are both thermodynamic factors needed to determine if a process is spontaneous. So if both enthalpy and entropy are needed to determine if something is spontaneous, then we need to find a way to combine both mathematically and observe the net results of each factor in a chemical process in terms of how well our reaction was able to disperse energy in total. And the way that we have of doing that is by using what's called Gibbs free energy, or delta G. So let's define the Gibbs free energy, or just free energy, of a system. So this is, of course, the change in Gibbs free energy of a system. So this is the change in the amount of energy that is freely available for a system to use to perform work. And that little like to perform work is kind of like a tag on, right? It's basically like the amount of energy that's actually available for the system to use. So not all of the thermal energy might be available to use, or be able to then like be changed or evolved to do work. Same with our entropy. So we have this idea of like our Gibbs free energy is calculating kind of like the leftovers of what's actually available to our system. Like what energy do we have to actually affect some kind of change with? So you can think about this as the chemical potential of a reaction. This is the amount of energy that is usable to enact a chemical change. So let's start with thinking about how Gibbs free energy could potentially relate to the idea of entropy and the second law, right? Because we're trying to talk about spontaneity here. That's the whole goal of this conversation in thermodynamics. Why do things just happen? So let's remind ourselves that if we were to think about, so let's derive an equation. If we were to think about the change in entropy of the universe, which we know must always be increasing according to the second law, that can be calculated at any time in theory if we looked at the change in entropy of some system, so for us, some reactant molecules, plus the change in entropy of the surroundings. Now note, this change in entropy of surroundings, this is something that we defined in our last video, right? We said that the change of entropy in surroundings is equal to the change in heat of the system, but with a negative sign, scaled by or divided by the temperature at which that system exists. So let's perform a substitution here. I can now say that the change in entropy of the universe is equal to the change in entropy of the system plus now the negative change in enthalpy of that system scaled by temperature. Okay, I hope we're starting to see why maybe this derivation is useful. We are now able to take the change in entropy of the universe, like the overall rule that tells us whether we're spontaneous or not. Did we increase the entropy of the universe? The second law. And we're now relating it to the thermodynamic properties of entropy and enthalpy of the system. Let's keep going with this. I don't like the fact that I have this like fractional term over here, so I'm going to multiply all sides of my equation by t. So this is going to yield T delta S universe is equal to T delta S system. And that's going to be minus delta H system. And because I typically want to like think about like the enthalpy change of my system and then not have to take the negative of it, like I want to be able to very quickly identify if I'm endo or exothermic, I'm going to move my negative over 2. So I'm going to divide both sides by -1. So now I get negative T delta S universe is equal to, and then just following the commutative property of addition, this is going to be delta H system minus T delta S. Surrounding. Nope, delta S system. There we go. Okay, we now have a means of relating the entropy of the universe to our thermodynamic properties of our system. And in fact, we now can say that by definition, this term, that negative T delta S of the universe, this is our way of quantifying the change in free energy of our system. So we can determine the change in Gibbs free energy of our system because that is what relates to the entropy change of the universe. So let's think about the implications here of this mathematical definition that we've made of free energy. Like, how does this relate to spontaneity? So if delta G is negative, this had to have been because if we're dealing with temperatures in Kelvin, there's no negative temperature. It had to have been because delta S was positive, because a positive number times negative yields a negative. Then delta S universe is positive. This is what obeys our second law of thermodynamics. So we would expect for this to be a spontaneous process. So negative delta G spontaneous. Inversely, if delta G is positive, then the delta S universe must be negative. So this would not be spontaneous. Because of that sign on delta S of the universe not being what we expect for our second law. So positive delta G, non-spontaneous, negative delta G, spontaneous. Okay. So now we have a way of finally determining quantitatively if a reaction is spontaneous based on looking at the sign of its Gibbs free energy. And its Gibbs free energy relates to the enthalpy and the entropy change of that system. Now, there's something that we haven't noticed yet, and that's this temperature term. So we are going to make a statement here that the spontaneity of a reaction or a chemical process is determined by the sign of delta G, which relates the enthalpy and entropy of a reaction at some temperature. Meaning that if we're going to talk about whether a process is spontaneous or not, we need to consider the temperature dependence of delta G. So recall we had a means of calculating delta G. This was equal to our negative T delta S of the universe, or if we look back at the kind of other side, we can express this in terms of enthalpy of the systems. This is delta H enthalpy of the system minus the temperature times delta S. So this is another means of expressing Gibbs free energy. One relates to the universe, the other relates to our system. Since we are chemists and we're talking about chemical systems, this is going to be the form that we use more often. And we see here that, yeah, the temperature at which this system exists is going to entirely determine whether or not we are spontaneous or not. So just a reminder, and also to give you some terms here, a negative delta G, this is spontaneous. At some T, we would call this exergonic, like exothermic, but instead we're talking about the net release of free energy. Whereas a positive delta G, this is a non-spontaneous process. At some temperature, this is endergonic, like endothermic. So I think I have red here for positive. There we go. So delta G is positive. We call this endergonic. And delta G is negative. Call this exergonic process at some temperature. And the reason why I give you this language is because you're probably going to hear it a lot in your biology classes. It's just talking about the free energy release or absorption of a system. So there's this temperature dependence on our free energy. So how about we consider a couple of different scenarios where like the signs for enthalpy and entropy are different, what the temperature might be. Scenarios where the sign of delta G can be predicted. So the first scenario we're going to start with is going to be a process that is exothermic and it increases in disorder, or the number of microstates has to have increased. Let's think about this means in terms of our free energy equation. So delta H minus T delta S. So if we are exothermic, that means that the sign of our enthalpy is negative, exo, releasing heat. And if we have an increase in the disorder, then this means that the sign of our entropy term is positive. So mathematically, this means that we are always going to have a negative number minus a positive number, which will always yield a negative result, regardless of what the temperature was, right? This could be 10 Kelvin or 1,000 Kelvin. And no matter what, we would have a negative number subtracting out this big positive term, which would result in a net negative result. So this means that at all temperatures, this process is spontaneous, meaning the sign of delta G is negative, and we would call this exergonic. If we want to think about this conceptually in terms of the second law of thermodynamics, if we're exothermic, we're dispersing thermal energy. And if we're increasing the amount of disorder, we are increasing the amount of disorder, right? Our entropy must be increasing. So that's a dispersal of microstate energy, right? So since our reaction has this double fold obeying of the second law, we disperse energy, then overall net, the reaction itself is going to disperse energy and thus do so in a spontaneous way. So this is kind of like our first idea of what it means for a reaction to be spontaneous. If we are in both cases dispersing energy, then it makes sense that our free energy should also be dispersed. So we would be exergonic. Now, what if we had the exact inverse? What if we were an endothermic reaction and the entropy decreases, meaning that the number of microstates that we can use to define our particles in our system gets smaller? So again, let's relate this back to our equation. Delta G is equal to delta H minus T delta S. So we have said that we are endothermic, so delta H is positive. So our system absorbs thermal energy, it concentrates it. And then we have said that delta S is decreasing. So this will be negative. So, what would happen here? Mathematically, this would always result in a positive number minus a negative number. Well, minus a negative, that's addition. So this will always be positive. Regardless of the value of temperature. Because no matter what, again, if temperature is 10 degrees Kelvin, I'm still going to be subtracting out a negative. And if this was 1,000 degrees Kelvin, I would still be subtracting out a negative, which would be adding, right? So in any case, I would always be seeing that this reaction would be concentrating energy. So what does that mean then? If this is always positive, then we can say that delta G is positive at all temperatures. So this process is not spontaneous. And we would call it endergonic. So again, no matter what, we are concentrating thermal energy when we're endothermic, concentrating, we're becoming more ordered. If you want to think about entropy that way, concentrating entropy here. So we are not going to be spontaneous. All right. What about the third type? What if we look at a reaction that does indeed disperse thermal energy, but it concentrates chaos, meaning it causes more order, becomes more ordered. So an exothermic reaction where entropy decreases, meaning the number of microstates decrease. So again, let's look at our equation. Delta G is equal to delta H minus T delta S. So exothermic, this is going to be negative. This is also going to be negative. So then is there any way that we can predict whether the sign is going to be positive or negative on delta G? As you might be able to see, the magnitude of temperature, how big the temperature is, how hot we are, is going to ultimately determine whether we disperse more thermal energy than we decrease our entropy. So we need to look at temperatures. At sufficiently high temperatures, the magnitude of negative T delta S is large, meaning we subtract out a number that is larger or I guess let's change it. Meaning we subtract out a negative. So if temperature is sufficiently high, the magnitude of that is large, meaning we add a T delta S term that is larger than the absolute value of negative delta H. So if we are at a high temperature, what would this result in? So if T is large, this would create this times this, which would be a positive number that is really big. So this would become like a large positive number. And if this large positive number is larger than the enthalpy, then we would see that overall we would have a positive delta G. So positive delta G, non-spontaneous. This was looking at if we are at a high temperature. What if we were at a low temperature? So again, we were looking at exothermic. And something that decreased in chaos or decreased the number of microstates. If the temperature is sufficiently small, then the magnitude of T delta S is less than the absolute value of delta H, meaning this would be too small of a positive term compared to the large negative that is the enthalpy of reaction. So this would result then in a negative delta G, which would mean we are spontaneous. Could also say we are exergonic. And another way to think about this is if our temperature is sufficiently small, meaning we're spontaneous at small temperatures, then we can say at small temperatures or at low temperatures, the reaction or the process is enthalpy driven, because enthalpy was the net thing that tended to disperse energy. Yes, we had to add away, right, because this is negative, we had to add away our entropy term, but at small temperatures, that entropy term is low enough that we still have an exothermic reaction. So we are enthalpy driven and spontaneous because we were able to disperse energy, just we were only able to net disperse thermal energy and not entropy. All right, lastly, we have the inverse. So what if we are endothermic and we increase the amount of entropy, meaning the number of microstates increases. So let's think about what this might look like, looking at our delta G equation. So delta G is equal to delta H minus T delta S. If we are endothermic, our enthalpy has a sign that is positive. And if we are increasing the entropy, this also has a sign that is positive, meaning that this whole term here will be negative. So let's look at if temperature is sufficiently large, then the magnitude of our T delta S term, meaning the size of this numerically, is going to be more negative than delta H is positive, which means that overall, if this is more negative than this is positive, then we would say that negative, our delta G is negative, which means that we are spontaneous or exergonic. Meaning here that this is the opposite. At high temperatures, the reaction is spontaneous, but it is spontaneous because it's driven by entropy. So at high T, the reaction is entropy driven. It may concentrate thermal energy because it's endothermic, requires heat, but it ultimately is going to have a larger net effect of energy dispersal by its entropy increasing. Which means then the inverse is true. If the temperature is sufficiently small, then the magnitude of T delta S is not negative enough to counter the positive delta H. So this means that our process here would be a positive delta G, so we would not be spontaneous. At small temperatures. So we would be endergonic at small t. So you have to look at like the actual value of your enthalpy and your entropy in order to determine if at some temperature your reaction is spontaneous or not. So in our next video, we are going to practice doing a calculation like this, meaning we're going to practice applying this equation, not there, but where'd it go? Here, yes, in pink, this equation. Okay, let's see here. And some color coding for reference. So at high T, non-spontaneous, low T, spontaneous. And the inverse is true here when we're endothermic, large T, spontaneous, small t, non-spontaneous. So we'll practice this in our next video, looking at a standard formation of sodium chloride solid. So see you then.